and all's well. Little slack and Donati, grabbing the power. Your arms are calling out. They wave like a swarm of sound. You pull the sound from scores of notes. You step the stage and take control. In a moment of silence, your body directs a pulse of wind. Von carry on Hecton, and you invite. Your arms are calling out. They wave like a swarm of sound. You pull the sound from scores of notes. You step the stage and take control. Those arms are calling out. They wave like a swarm of sound. You pull the sound from scores of notes. You step the stage and take control. Control, 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 control.
All right, so last week we introduced the notion of binary search trees. We've been looking at trees and binary trees for the last week, but then we started to add even more structure into it so that we could exploit that structure for efficient operations. And the binary search tree property that we introduced was that everything has a key, right? And everything in the left subtree is less than that key, and everything in the right subtree is greater than that key. That's an inductive property that holds for every single node. So for example, if you look at node 20 here, everything in its left subtree is less, everything in its right subtree is greater than it, right? We don't allow duplicates, because if you do allow duplicates, well then you can always break ties arbitrarily, or you can go ahead and break ties to the left side or the right side, as long as you are consistent about it, okay? So how are we able to exploit this structure? Well, it's very similar to binary search. That's why we call them binary search trees. That all you need to do is start at the root, and if you're searching for 45, you know that it's not here, so all you need to do is go left, right? And then 45 is greater than 40, so you go right, and you finally find what you're looking for. The entire process ends either when you get lucky enough and you find what you're looking for example, searching for 50, you're done, right? And you only made one comparison in that case. To compare it to 45, only made 1, 2, 3 comparisons, right? And sometimes you get unlucky, right? You get all the way down here to the end of the tree, in which case you've made 1, 2, 3, 4, 5, 6 comparisons in this case, or in general, order D comparisons, where D is the depth of the tree. You could also get unlucky in an unsuccessful search. For example, searching for 13. You get down here to 12 and you search and look at its right child, and there is no right child, and therefore 13 is not in the tree. You would result in an unsuccessful search and say, no, it's not in the tree. Okay? So what I want to do today is start on an actual implementation of a binary search tree in Java. I am not going to go with the binary tree that we were working with before. I'm going to reuse some parts of it, but I'm not going to inherit from it. I'm not going to put it into an inheritance hierarchy, because a binary tree, yes, a binary search tree is a binary tree, but the interface here would make it not so. What does it mean to have a pre-order traversal of a binary search tree? What does it mean to have a post order or a BFS traversal of a binary search tree? It doesn't make that much sense. So I want to start new here and not have to lock myself into an inheritance hierarchy. What you could do is you could make it so that you own, via composition, private binary tree, right, there we go, key, right? Via composition, you would own a binary tree, and then you would change the interface so that you are only interacting with it with things that make sense for a binary search tree, right? Much like you did in one of in your lab last week, where you used a linked list inside of a stack or a queue so that you could reuse the implementations, but you didn't lock yourself into this inheritance hierarchy, because a stack is not a linked list and a linked list is not a stack. Right? So you use composition instead. I'm going to go ahead and start from scratch though. Right? I'm going to simply just have a binary search tree node here that is a root. Okay? Good enough. You also might want to keep track of the size of the tree. Now, we didn't do that with the other example, binary tree, because we never actually implemented anything to get stuff into the tree. I just built an ad hoc tree so that we could look at the pre-order, post-order, in-order, and breadth-first search algorithms. But now maybe we do want to keep track of the size. Right? We'll come back to that, though, later. Okay? For now, all I want to do is create a binary search tree and then put stuff in, take stuff out. So public, actually I'll just leave the constructor for now. We'll come back to the constructor. But I definitely want a public void add or insert. Right? Let me go ahead and call it add, because that's what it is, an element x. Now, does it make sense to add element at index and then take it in element index, int index? Right? Does that even make sense? No, because it's a tree. There are no indices. Would it make sense for your project that's due this Friday to allow somebody public access enough to add an arbitrary element to an arbitrary location? That doesn't sound like a sorted list to me. Right? So, no. You just simply want to add it. We will take care of that. I'm the tree now. I'll take care of that for you. Right? I'm the tree. I know what a tree is. I know what my left children, root, right children, et cetera, are. I will take care of that for you. Okay? Leave a nice to-do. Implement. Implement. There we go. And then maybe a retrieve method. Right? Public, say, Boolean. Right? Contains. Right? There we go. What I'll do is like this. Now remember that we are parameterizing this so that it can hold any type. Integers, strings, invoices, people, et cetera, et cetera. I'm simply going to just ask, do you have this element right here? Okay? True or false? I'm not going to actually return the element because, I mean, you could do that in some sense, but remember that this is just a key value kind of thing where I'm just going to have some sort of a key here, and then that maps to the actual data that I want, the value over here. Okay? That would take a little bit more of a design than we're going to do in this class and in this demonstration. All I simply want to know is, do you contain that element? Okay? All right. So which one should we implement first? Well, we got to get stuff in there first, right? I'm going to go ahead and go backwards, though. Let's go ahead and do the easier one first. Let's just assume that this has been done for us already. Okay? I want to know, do you contain this element or not? Okay? Let's come back over here to our visualization. I want to know whether or not you contain 50. Well, you start at the root. Yep, we're done. Stop. One comparison, you return true. Otherwise, I want to know, do you contain the element 45? Right? What do? I start at the root. That's not it. So one comparison. I go to the left child because 45 is less than 50. Right? Is that it? Nope. Two comparisons. So where do I go? I go over here to the right child. Three comparisons. At most, I'm done. Right? What happens in an unsuccessful search? You keep going, you keep going, you keep going, you keep going, and then finally you fall off the edge of the tree. In terms of Java, what are you doing here? You are keeping track of the current node that you're standing on. There's this guy standing on here, and then he's going to walk down over here. Right? Then he's going to walk down over here, dot, dot, dot. Eventually, when he falls off the tree, this guy is null. Right? So that means that we're going to want to keep track of a current node. Right? Let's go. Actually, let me go ahead and resize this right here. Move this down, move it over, and let's go ahead and get rid of all this. There we go. Now let's outline that process that we just identified. I'm going to have a current node. Where do I start my current? Where do you start this entire process? The root of the tree. By the way, a corner case. If the root is null, then no tree, no elements, it's false. So keep that in mind. Otherwise, I'm going to start at the root. And then what I'm going to do, I'm going to make a comparison. If the current's key is equal to, and here I'm search for k, right? If that's equal to k, then I'm done. You were searching for 50, you found 50, you're done. Output, the current node, the yes, the true, whatever, right? Output current. There we go. Otherwise, the current's key, or the thing that you're searching for, is less than the current node's key. So I'm looking at 50 here, but the thing that I'm looking for is less than 50. So where do I go? Left. Pseudocode here, I'll simply just say go left. Go to the left child is what I mean. Else if the thing that you're searching for is greater, or current.key, excuse me, is the current key is less than the thing that you're searching for, or another way of saying that is that the thing that you're searching for is greater than the current key, then where do you go? You go right. There we go. That's one iteration though. Right? That was just looking at this 50 and you go, yes, that's it, or go that way, or go that way. How do we repeat ourselves? Yeah.
While it has children?
Okay.
Or like while it has
Oops.
like branches?
Let me go ahead and move this. And we're definitely going to want to nest this somehow. Right? Inside of and you immediately jump to a while loop. Why did you use a while loop?
We don't know how big this tree is.
Because you don't know how big the tree is, you don't know how deep the tree is, you don't know how many iterations you're going to go for. Sometimes it's just one. Sometimes it's 1, 2, 3. Sometimes it's all the way to the depth. So a while loop is more appropriate than a for loop. Yeah?
Just as a question I would like to ask, because my first thought was while it has a branches period, because I don't know if it's possible to have 3 or 4 branches. Is that possible or no?
That would be called a ternary tree. If you had more than 3 children, or 3 or more children, that'd be called a ternary tree. If you have 4 children, that would be called a quaternary tree, right? Right? There are things called B trees that have up to B children, right? And then they have more properties than that, but we're only looking at binary trees. Why are we only looking at binary trees? Why aren't we looking at ternary trees, right? What about binary trees is different than ternary trees? Everything over here ends up being log base 2 of n. What about everything over here? Just predict what you think it might be. Log base 3 of n. With big O analysis, is there any difference between these two? Nope. Why? Because of the change of base formula. So why do 3 when 2 do not enough, right? Or whatever it is, right? So, but there are things called B trees, but they are therefore ensuring balance, right? We won't talk about that in this course, though. All right, so what's the condition here? While? Well, while you're still sitting on this tree and you're not null, right? So while the current is not equal to null, or in pseudocode speak, phi. There we go. At the end of all of that, you've fallen off the tree. You didn't find what you were looking for, 13. So what should you output?
No.
Output no, false, null, whatever your flag value is for an unsuccessful search.
Error.
Right? Error, throw an exception maybe? Yeah. Those are all perfectly valid answers, right? Just a design decision. So let's go ahead and take this algorithm and implement it over here with respect to our Java implementation. The first thing I need to do is what? Create a current node. So binary tree node for elements of type T, and I'll call it current instead of cur, because I'm not paying by the character, right? This.root. That's where I start. Now remember, I asked you to keep in mind what happens when you've got a null tree, when you've got an empty tree. Right? I've got my while loop here. In the end, I will return false. Right? While current is not equal to null, this is just a direct translation of my pseudocode. Right? While the current is not equal to null, and the output at the end is going to be false. So what happens with an empty tree already, without me looking at anything else? We've taken care of it, right? It's going to return false if this root is null, right? Can you have 13 in an empty tree? No. Can you have 42 in an empty tree? No, right? So that takes care of that corner case already, but be thinking about those corner cases, okay? How do I translate the rest of this stuff? Well, if the current's key is equal to k, right? If the current dot get element, there it is equal to the key here in this case is x, then output true. Right? Be careful. Equals equals. Is that ever valid in Java? It's valid for integers, small I integers. It's somewhat valid for small d doubles. Is it valid for strings? Nope, this is a common mistake. Is it valid for invoices? How do you know that this invoice is equal to this invoice? What is this thing doing right here? It is comparing memory addresses. Is that thing the same thing as that thing in memory? Right? That's not what you want. How do you compare strings? Yeah.
You could do like dot compare to.
Oh, okay. If it were comparable, but do I know anything about T's? Nope. So, but I do know that they're objects, so maybe equals? That seems okay for now. We'll come back to it in case we need to update it. Okay? So if that thing equals that thing, every object is going to have an equals method. It is defined way up here in the hierarchy. Every object has an equals method. Just like every object has a hash code method, a get class method, et cetera, et cetera. Okay? That's good enough for now. Right? Else if some condition, else if some condition. Remember that I go left or I go right. Now let's fill in those conditions. Let's remind ourselves what they look like first. If the thing I'm searching for here, is less than the current's key, then I go left. Right? So how do I make that comparison? The thing I'm searching for is x. If that is less than current.getElement, right? Can I do that with anything other than integers and doubles and et cetera? Can I do that with strings? Certainly not. Can I do that with arbitrary objects? Certainly not. Not even memory location comparisons here. Yeah?
That's why I was saying comparison earlier.
Hold on, yeah.
Strings you can do less than or equal to, but
Hold on to that thought because we're still not going to be able to use compare to. That requires the comparable interface, all right? So let's go ahead and fill in the rest of this, though. This the current element, if it's less than the key, so in other words, take this entire thing and flip it around, is less than x, then you go right. Now, what does it mean to go left? We'll worry about fixing that here in a second. What does it mean to go left? Current is equal to current dot get left child. There we go. I just update what I'm standing on. The guy walks down to the left child, walks down to the right child. So current is equal to current dot get right child. Now, do I have to check to see if there is a left child or a right child? No. If it's null, then that's what breaks me out of this while loop. Right? Cool. Right. Strictly speaking, do you need this if condition? It's either equal, strictly less than, or strictly greater than. Right? I could get away with this. Right? I don't want to get away with that until I have actually fixed this. Okay? All right, so help me out. Dot equals, that works for equality. Right? Somebody suggested that we use a compare to. That would require me to change this so that t extends comparable for elements of type t. Right? Now I can use compare to. But is everything necessarily comparable? No. Right? I don't want to do that because that's too much of a restriction. If you remember way back when we did a polymorphism, right? We kind of played this balancing act. Too general and you didn't have enough information about it. Too specific and you didn't and then you'd have to write a binary search tree for strings and a binary search tree for integers and a binary search tree for doubles. So we found this healthy medium here. Right? Ultimately what we did was we used here's two objects, elements of type T and type T. Do they go like this, or this? Right? I don't know. Right? I don't know how to do this because I don't even know what they are. They're just T's. I'm going to hand it off to somebody else that does know what they are. That somebody else is a comparator. Excellent. Right? So I'm going to make a private comparator, CMP, spell correctly, there we go, comparator, move it up here, and also parameterize it. Because it can't just be a comparator for whatever. It has to be a comparator for elements of type T. Right? How do we get this into our binary search tree class? How do you get anything into your class? With a constructor. Right? So we will take a comparator, CMP. This .cmp is equal to that .cmp. And I'm just going to go ahead and import this, java.util. Okay. When I create a binary search tree, I now need to provide it let's open up the demo over here. I need to provide it a comparator. So I'm going to go ahead and get rid of all of this here. Binary search tree. I'm just going to go ahead and keep it for integers. All right. And I'll just call it T. Get rid of this. New binary search tree for integers. You don't have to repeat that. You can elide it away. Right? But now I'm going to have to provide it a comparator. I already wrote one, tree utils.cmp int. Right? Take a look at what that looks like. There it is. All it's doing is using the compare to that you suggested before. Why? Because integers have that built in. Right? In ascending order, non-decreasing order. Negatives first, then 0, then positives, right? In ascending order. Right? And that's the default behavior there. If you wanted it different, then you'd have to build a different comparator. But that's good enough for me for now. Right? That matches our diagram over here, actually. That's why I did it that way. Right? And guess what? I already built that tree. Right? We'll get to that in a second, though. Okay. By the way, do you think I drew that diagram? No, I generated it with my code, right? I'm not going to do all that work. No way, right? All right. So that almost compiles, except that now we need to rephrase this in terms of the comparator. I'm going to give x and the current node's element off to the comparator, and it's going to return something negative, positive, or 0 depending on the relative ordering of those two things. This dot CMP, you keep the same order, and you keep it less than. There. That means, this dot CMP dot compare, there we go. That means that X comes before the current element, right? The current node's element. Well, I can go ahead and get rid of this for now, or I could go ahead and rephrase it in terms of the comparator. This dot CMP dot compare current dot get element X, and if that is less than 0, then you go right. Note here the only difference is me changing these things around. It's still going to be strictly less than 0, strictly less than 0, because if you change them around, obviously positives become negatives, negatives become positives. Zeros stay the same. Having done that, I'm going to immediately get rid of it because why do that? Why make 2 calls to the comparator, right? Yeah.
You can actually notice down to one call for the variable for it.
Good. Hold on to that thought for a second. I want to go ahead and get rid of this one right here first. Right? If I'm using a comparator, that might be different from dot equals. I want to be consistent about this. If this is equal to 0, then that means that those two things are the same and you found what you're looking for. You found that, that invoice that had that particular salesman, or you found that invoice that had that particular total, right? Invoice that had that particular total, because you could have several. Right? What do? You break ties somehow so that you don't have duplicates. With an invoice, how could you break ties? Code, something that's unique. Database integer, something that's unique, right? Etc. And good observation that no, we're not going to make 2, 3 calls to this comparator. What are we going to do? We're going to make 1 call to this comparator. Int result is equal to that. And then you simply just ask yourself, is the result 0? Or is the result strictly less than 0? Or is the result, let's restore this if for just 1 second here, if the result is greater than 0, then you go right. And then once again, you don't need this if statement here, but I'll go ahead and leave it in, just for demonstration purposes. Okay. There, now it's nice and pretty too. Do we know it works? Let's go back over here to the demo class here. All right. So I want to ask t.contains 42. What should I get back here? Well, is anything in there yet? No, so false? Oh, it works. Is that testing? Is that proper testing? No. All right, this is always going to be an empty tree because we have not added the ability to add anything into it yet. Right? We haven't done this up here. So let's hold off on that testing for a while. We need to be able to add stuff before we can verify that we added it. Right? So let's come back over here and think about this again. Before I erase my pseudocode here, let's think about how this might look. I want to add 13. Well, actually, here, let's say add 45. So how would you go about doing it with this particular tree here? You would come in here, 50, that's not it, right? Go down over here. It needs to, 45, the thing that I want to add is less than 50, so it should go over here in this left subtree. Could I have done this instead? Could I have said, all right, 45 is my new root, and I'll just go ahead and attach it there?
No.
That's not a binary search tree. All right, fine. You got me. Nope, sorry. Get rid of it. 45, okay, fine. I'll make 50 its left subtree. That ain't a binary search tree either. Right? So what we're going to do is we're going to cause the minimum amount of change to the topology of this tree. We don't want to mess it up too much. I'm always going to insert as a new leaf all the way down at the bottom. I need to find out where it belongs. So I come in here and I say 45 is less than 50, so it belongs somewhere in this left subtree. 45 is greater than 40, so it belongs somewhere in this right subtree. Uh-oh, there it is. Do we add it? not if we're disallowing duplicates, right? So what do we do? Throw an exception, replace 45 with 45, okay, right? Or what I'm gonna do is no op, right? Noop, no operation. We just won't do it. Right? That's certainly optional. That's certainly an option. Right? Okay, let's go with something that actually does make sense. 13. Insert. 13. All right, well, certainly it's not a duplicate, because if it were a duplicate, where would it belong? Right here is the right child of 12. Hey, that's where we end up inserting it. So guess what? As a first step, I'm going to search for where it should be if it exists. If it exists, instead of outputting it, what am I going to do? Well, if it already exists, do I want to add it again? Nope. Nope. No op. Right? Otherwise, I get out of this loop here and it does not exist. So insert as leaf. ... How? Right? So I could it could start with a cut and paste of this right here. Find out where it belongs. Let's try that. All right? There we go. So I've got a current, and instead of returning true, I'll just simply return for now. Right? Instead of returning false, I need to insert at the current node. ... Right? Am I going to be able to do that? Current dot add right child. I don't have anything like this yet. It's a set right child anyway, right? Set right child. Am I going to be able to do that with current? What is, look at the code real close. What is current at this point in the code, on line 31? I broke out of this while loop, right? So therefore current is null. Can I invoke this on a null object? No. Let's come back over here and realize what's happened. We went through this tree, 1, 2, 3, 4, 5, and now we're right here. What do I need to do to make a brand new node right here? I need to set 12's right child to this brand new node, and then set this brand new node's parent to 12, etc. Right? That means that I need to keep track of this node right here and not lose it like I've done. Right? I've got current, which is null. So what should I do with this guy right here to keep track of him? Well, if it's not the current one, it's the previous. So I'm going to keep track of two nodes, the current one and the previous, because I know that if I fall off this tree and current is null, I still have that previous in order to make a reference to it. So let's do that. Previous, right? And this is why people usually use prev and cur. Oh, everything that lines up so nice there, 4-letter words, right? We're not paying by the character though. Right? It's not going to line up very well, but whatever. Do I set that equal to the root? No. When I start out, the current is on this node right here. So where's previous? Well, in terms of Java, it's null. Right? And so I'll set it equal to null. Okay? Every time I go left, before I go left, what should I do? Update the previous to be the current. Then you can go ahead and replace the current. Every time you go right, update the previous to be the current so that you keep track of it. Now when I get out of this loop, guess what? Current is now null, but what is previous? The parent. So step 1, create a new node. So binary tree node, T, new node or new leaf, right? Remember that it's a leaf, is equal to new binary tree node, parameterized on the same, and we're going to hold X, Remember, the thing that we're asserting, don't lose the forest or the trees here, is x, right? No pun intended, right? New leaf. Now what do I need to do? I need to first of all set my parent. New leaf dot set parent to, not the current, but the previous. BS. There we go. Then what? Now new leaf needs to be previous's left child or right child. Which one is it? Yeah.
That's a comparison you gotta make.
Yeah, that's yet another comparison here, right? So let's go ahead and make this a comparison. And I'll just go ahead and grab this code here. And we know that it's not equal, because if it were equal, guess what we would have done? We would have already exited this method. Otherwise, we know that if x is less than not the current, but the previous dot get element, if that's less than 0, then that means that x comes first. So should it be the left or the right child? Left or right? And then I've got my else here, left or right. Well, whatever it is, it's the other one, right? And then I'll return. There we go. So x, the thing that I'm inserting, is less than the previous. What does that tell you about this? Here, look at it from a general generic point of view here. Here's the previous, and x is less than the previous. So where does it go? Left. Okay? So x is left, I go left. So previous dot set left child to be my new leaf. There we go. And which one is this? The other one. Right? And it's not a question anymore. We know what it is. Previous dot set right child to be the new leaf. And return. Now, how could we make this a little bit more functional, a little bit more, give it a little bit more information, right? This void method here, well, I could be returning something. Typically what is returned is a Boolean value here. That Boolean value indicates whether or not an operation happened or no operation happened, noop, right? So inserts the given element x into this binary tree, right? Returns code true if the insertion was successful, right? Changed the tree, right? False if no operation occurred. I mean, that's a little bit more, flexible, right? Because I can choose to ignore that. I don't care if you're making a change or not. I just want to make sure that that thing is in there, right? Or you can go ahead and use this in conjunction with, say, contains to have some more information here, right? In which case, did it have an effect here? False. There we go. Did it have an effect here? Yes, we inserted it. True. There we go. Okay. Let's try it with a little bit of a demo over here. Does it contain 42? Well, it's still going to be false. All right, fine. Let's go ahead and insert it. T.insert, or what was it, add, right? Add 42. And let's check it to see afterwards whether or not it had an effect. What should I expect now? False, it's not in there. I put it in there. Now it should be true. Crossing my fingers here. False exception. Cannot invoke get element because previous was null. Previous is null? I made accommodations for current being null. Why would previous ever be null? Let's go ahead and jump into that, right? On line 44. Right? So, think about this from the perspective of what the tree looks like before we do anything with it. What does the tree look like? There's nothing in there. So what is root? There we go. Root is going to be, it's an empty tree. There's nothing there. So root is null. Walk through the code with me. Previous is null. Current is null. Does this while loop ever execute? Nope. We create a new leaf. We set its parent to the previous null. That's fine. Right? And only when we get down here to try to say, all right, does it belong to null's left child or null's right child, do we end up hitting a snag? What did I forget to do? Think back to linked lists. When you create a linked list and put something into a linked list, right? If everything is normal, right, you've got like 5 elements in there and you want to put it right here, it worked. Right? You had to think about corner cases. One of those corner cases was, what do you do about an empty list to begin with? You create a new head as a special case and you set the new head. What happens here? If you want to add something, do you need to check to see to an empty tree? If this dot root is equal to null, then it's an empty tree. What do? Steal this stuff down here, right? And don't call it new leaf. Well, it is a leaf technically. New root is equal to that. And then this dot root is equal to the new root. And did it have an effect? Yep. So I should return true. Now let's go back over here and see if it works. Remember, false, put in 42, and now it should be true. Ha, neat. Done, it works. Nope. Let's go ahead and add something else. T.add, I don't know, 50. Where should that go? To the right child, right? Well, all it tells me is true. I got in there somehow. Right? Do I know if it's a left child or right child? No. Okay. Add something a little bit less. 10. Did it get in there or not? Yeah, okay. I've got a little bit of assurance that this is correct. Is that enough? Probably not. Right? So, ideas. Yeah.
You could have it say both the true result and what it's less than or what it's conditioned for, and you know where it is in the tree.
I could repeat basically the entire implementation as a test suite. I could do something like that, but I want to keep it simple. Let me come over here to your tree utils, and let me go ahead and put all of these values here into a big giant string, parse them all out, and then insert them. I called it add instead of insert. Right, there we go. Okay. That will give me this large BST that looks somewhat familiar. Guess what? There it is. If I insert in that order, this is the tree that I get. Right? Let's go ahead and come over here to the demo, and instead of a new binary search tree, I'm just going to say tree utils dot large BST. Now, in terms of actual testing, what does this mean? This would mean that you are creating this tree just like I did before with that binary tree up here, right? Where I manually built it, from the ground up, set every single child, set every single parent, et cetera, et cetera. This is actually what I would do in, say, a JUnit test. I would make a reasonably sized tree, and then I would make sure that everything got in there, that everything is as expected. I didn't want to do that for this binary search tree. Because I wanted to test two things. I wanted to test both insert and that contains method altogether. All right? So one way of doing that is, let's go ahead and get rid of, that's not binary tree. Here we go. Everything's compiling now. Not everything is compiling over here though. The reason that it's not compiling is I located this stuff outside. So just for the purposes of testing, I'm going to temporarily make this into a package protected value. Let me show you what it looks like now. All right? So it built a large BST. I like visualizations. Right? So what I did before I came here is that I created an empty tree. There we go. And I took those values and I inserted them using a secondary tool, which is what we've been recommending that you do this entire semester. Use a secondary tool to test stuff, right? Use your calculator, use Wolfram Alpha, use an online CSV data converter, et cetera, as much as you can. I'm going to go ahead and insert all of these values. Oops. What? There we go. Nothing is, there we go. Fast forward, of course, and this is what it should look like. That doesn't really help me for my implementation here, but what I did is I added some code here that would result in some sort of a visualization. All right, I'm using LaTeX, which is and a TXI environment in LaTeX, which is a diagram drawing tool here, and it's simply just going to generate code that I can then render in LaTeX. Right? Anybody doing LaTeX for 235 right now? The discrete math. All right, great. If you've never learned LaTeX, learn it. But you know, it's not, unless you're going to go into academia. It probably is not. It's not used in industry. If you're going to learn LaTeX, you also should learn TXI, which is a drawing tool, a diagramming tool. System.out.println tree utils dot toTXI t. There we go. Let's go ahead and run this now. Everything compiles. Oops. Yep, it's all there. Right. There's what it looks like. And by the way, I've got overleaf over here. Let me switch back over to the editor and show you that indeed it is exactly the same tree because I didn't want to screw up. Right. There we go. Switch over to PDF, recompile it, and there it is again. Right. I wish I had zeroed that out so that it was more dramatic, but there it is. Right. Now, is that the tree that you're expecting? That looks like the tree I'm expecting, right? If I were to insert stuff in that order, I would get this tree. Two tools now have verified that this is correct. Technically, my TXI drawing tool that I created was a secondary tool as well. Right? So I'm convinced that this actually works, right? Do I have 100% proof? 235, folks. Do I have 100% proof that this works? No. You would need a mathematical proof. And there are techniques that they're called formal verification or formal analysis of a software where you do come up with a proof, which is another program that verifies the proof of this program over here, the correctness of this program. Guess what? You just shifted your responsibility. Now you have to prove that your proof is correct. Okay, write another program to prove that that one's correct. Now you have to write another proof that that proof of the proof is correct. It's a never-ending cycle, and that leads to metamathematics and the Gödel's incompleteness theorem. Don't worry about it, way beyond the scope of this course. We have 99% assurance that this is correct, which is good enough. Right? Remember, in engineering, what's better than good? Good enough, and this is good enough. Right? All right, we'll continue there on Wednesday.